Welcome back to this lecture series on deep learning. In this lecture, we will discuss what are all the key challenges we are facing in deep learning and how we are going to overcome those challenges. We'll see one by one. First, introduction and why challenges matters in deep learning. Deep learning is powerful but not always practical in real world scenarios. That means, although deep learning, that is DL, has achieved great success in many fields such as image recognition, natural language processing, it is often hard to apply directly to real world problems. This is because the conditions in which deep learning works best, such as large scale, clean labeled data sets, are not always available outside of research labs. That is the main challenge. So, major challenges include a need for huge labeled data. That means deep learning models depend heavily on massive amounts of labeled data to learn the first point, learn patterns effectively. Collecting and annotating such data sets is a costly and labor intensive process. Second one is poor generalization to unseen data. That means once the data sets are trained, what will happen means the second point, poor generalization to unseen data. Once the data are trained, DL models often perform poorly when tested on real data that is slightly different from what they have seen during training. This limits their reliability in dynamic environments. Next, lack of comment. That is the third point is lack of logic-based reasoning. Most DL models most DL models learn statistic patterns from data but struggle to incorporate human like reasoning, rules, or prior knowledge. This makes them weak in areas requiring logical deduction or step by step reasoning. And the fourth challenge is high computational cost and data demands. Training deep models with many layers. So, if you are taking one layer one, two, three, training deep models with many layers takes enormous computational power and energy. This makes them unsuitable for devices with limited resources. Understanding these helps drive innovation and research in better models. By identifying and analyzing these limitations, researchers can focus on developing more adaptable, efficient, and robust AI systems that are better suited for practical deployment. The first challenge is too much training data needed. Training data needed is means that data models need millions of labeled samples to perform well. Deep learning models are designed to learn from large data volumes, often needing millions of annotated examples to capture complex features. This becomes a barrier in fields like healthcare or astronomy where such data is rare. Labeling is expensive, time consuming, and impractical for many domains. And manual annotations involves human effort, domain expertise, and time, making it costly, especially for highly specialized data such as medical images or legal documents. The second point, and how to overcome this challenges means transfer learning. Use pre-trained models and fine tune them. That means instead of training from scratch, what will do is transfer learning. The transfer learning means it uses models pre-trained on large data sets like ImageNet and adopts them to new tasks with relatively little data, saving both time and effort. Next, semi-supervised learning. Learn from both labeled data and unlabeled data. By training on a small labeled set and a large unlabeled set, Models can still achieve high performance while reducing reliance on manual labeling. Next, data augmentation. Artificially increase data size using variations. Techniques like flipping, in this case, techniques like flipping, rotating, or adding noise to existing data can effectively increase data set diversity and help models generalize better. And if you are taking the example, a model trained on ImageNet can be fine-tuned to classify satellite images of crops, even if there are only a few thousands of labeled examples. This drastically reduces data requirements while maintaining accuracy. The second challenge is the next challenge is poor performance on unseen data. That means out of distribution. Models assume test data similar to training data. Deep learning models work well when the input data during testing is drawn from the same distribution as the training data. If not, their performance can drop significantly. And real world data changes over time, location, conditions. In practical applications like speech recognition or weather prediction, the input data may change depending on context, geography, or time. These distributions shift to break the assumptions made during training. Next, lead to performance drops when data shifts. When faced with the out of distribution, this out of distribution we can call it as OOD, out of distribution data that is somewhat different from the training set. The model may produce unreliable or inaccurate predictions, which is risky in critical applications like healthcare. And how we are going to overcome these challenges? The first one is domain adaptation. Adjust model for new environments means domain adaptation techniques align the feature distributions of the training and data set test data so the model can perform well on both. Next, robust training. Train with diverse or adversarial data. By including a wide variety of data during training or using adversarial examples, models become more resilient to unexpected input patterns. Next, online learning. Continuously update models as new data comes. That means online learning enables model to keep adopting over time by learning from new incoming data, thereby maintaining the relevance. Say, for example, a weather prediction model trained in India may fail in Europe due to differences in climate and data patterns. Using domain adaptation techniques, the model can be tuned to perform well in European region too. Next challenge is lack of logic reasoning. Deep learning models don't understand rules and logic. That means neural networks or statistical models that learn correlations from data but lacks the capacity to perform step by step logical reasoning or a symbolic manipulation like human what we are doing it, and cannot easily perform symbolic reasoning or decision trees. And the task requiring, that is the second point, is cannot easily perform a symbolic reasoning and or decision trees. Tasks requiring reasoning, such as diagnosing diseases based on symptoms, often involve following logical steps that the deep learning models struggle to represent or infer. And how we are going to overcome these challenges? Combine DL with the symbolic AI, neuro-symbolic models, we can call it as. By combining deep learning with the symbolic reasoning, such as logic programming or knowledge graphs, models can both learn from data and reason over it, and introduce rules or constraints in output layer. Incorporating domain knowledge as constraints can guide the model to produce outputs that make logical sense even in complex scenarios. Next, use graphical neural networks or reasoning modules. These architectures are better at learning relationship and performing structured reasoning tasks. And if you're taking the example in medical diagnosis, integrating logical reasoning like logical rules like if fever and cough, then check for flu. The person is affected with if we are writing if fever and cough, then check for whether the person is affected with flu or not. Alongside, deep learning predictions result in more accurate and independent, interpretable outcomes. Next challenge is high complexity data and resource demands. The first point is deep models is equal to more layers and more parameters or and is having higher training time cost. As deep networks grow in depth and complexity, the number of parameters increases dramatically, requiring more memory and computational power. Power is more power is needed. So this is one drawback, especially during training. And without enough data, overfitting occurs. High complex models trained on a small data set tends to memorize the data instead of learning general patterns, resulting in poor performance on new data. And how we are going to overcome these two challenges? Model compression, that means prune or quantize model weights. Compression techniques reduce model size by removing unnecessary weights. Unnecessary weights will be removed by using the model compression techniques or lowering precision without significant accuracy loss. Next, efficient architecture. By using mobile net and efficient net, etc., we have to use it. These models are specifically designed to offer a balance between performance and efficiency, making them suitable for resource constrained environments. Few short learning. The third challenge, that is the third solution is few short learning. It enables learn from very few examples. Few short learning enables model to generalize from very limited examples, useful in domain with the scarce data. Using and the example for this case is using mobile net. Using the mobile net, real-time object detection can be done on mobile devices without needing large GPUs, without needing here GPU, large GPUs not needed if you are using the mobile net, enabling practical deployment in resource limited areas. And next, coming into the conclusion, driving the better deep learning. These challenges will motivate new research and innovations, and recognizing and addressing these challenges leads to new strategies and techniques that make deep learning more practical and accessible. Use less data via smarter learning methods. Methods like transfer learning, few shot learning, and self-supervised learning reduce dependency on large labeled dataset. Better adaptability and to unseen data. Robust and adaptive models can maintain accuracy even when tested on data outside the training distribution. Integration of logic plus learning, that means neurosymbolic approaches allow deep learning systems to reason logically while still learning from data. Next, efficient training with low cost computation. Research into lightweight architectures and training optimizations make it feasible to deploy AI even on edge devices. The main goal is build scalable, robust, and intelligent AI systems. The ultimate aim is to design AI systems that are not only accurate but also flexible, interpretable, efficient, and robust across diverse real world applications. Hope everyone understood about the challenges in deep learning and how we are going to overcome these challenges. The remaining things we'll discuss in the next lecture. Thank you.